In the video on sp3 hybridization, we saw carbon was bonded to 4 atoms. In the video on sp2 hybridization, we saw that carbon was bonded to 3 atoms. And in this video, we're going to look at the type of hybridization that's present when carbon is bonded to 2 atoms. So if I look at this carbon right here and the ethine or the acetylene molecule, this carbon is bonded to a hydrogen and it's also bonded to another carbon. So we have carbon bonded to only 2 atoms. And the shape of the acetylene molecule has been determined to be linear. So we have a linear geometry. We also have a bond angle here. This bond angle is 180 degrees. And so we must have a different hybridization for this carbon. We have a different geometry, a different bond angle, and a different number of atoms that this carbon is bonded to. And so to find our new type of hybridization, we look at our electron configuration already in the excited state. Right? So we have carbon's 4 valence electrons represented here in the excited state. So 1, 2, 3, and 4, and we're looking for 2 hybrid orbitals since carbon is bonded to 2 atoms. So we're going to take an s orbital, so we're going to promote an s orbital in terms of energy, and we're going to demote a p orbital, only 1 p orbital this time. So we have an s orbital with 1 electron, a p orbital with 1 electron. That's going to leave behind 2 p orbitals. Each one of those p orbitals has 1 electron in it. So we have carbon's 4 valence electrons. But this is no longer an s orbital because we're going to hybridize it with the p orbital to make an sp hybrid orbital. This is no longer a p orbital because we're going to hybridize it to form our sp hybrid orbital. And so this is called sp hybridization. So this is sp hybridization because our new hybrid orbitals came from 1 s orbital and 1 p orbital, like that. So this carbon right here is sp hybridized since it's bonded to 2 atoms, and this carbon right here is also sp hybridized. Let's think about the shape of our new sp hybrid orbital. So let's get a little bit of room down here. So once again, we know an s orbital is shaped like a sphere, right? So we took 1 s orbital and we took 1 p orbital, which is shaped like a dumbbell. Right, and we hybridized these 2 orbitals together to give us 2 new hybrid orbitals, 2 sp hybrid orbitals. I'm going to go ahead and draw in an sp hybrid orbital here. And once again, we're going to ignore the small lobe, right? So we're going to ignore the small lobe, and when we draw our picture, only think about this bigger frontal lobe here. And when I think about the percentage of s character, right, so we use 1 s orbital and 1 p orbital. So that means it's 50% s character and 50% p character. And this is more s character than in the previous videos, right? So in the video on sp3 hybridization, we were talking about 25% s character. In the video on sp2 hybridization, we talked about 33% s character. And then for these hybrid orbitals, we have even more s character, up to 50%. And since the electron density for an s orbital, right, there's increased electron density closer to the nucleus for an s orbital than for a p orbital, that means that this lobe here, right, has increased electron density closer to the nucleus, which is one way to think about why these bonds get shorter as you increase in s character. So in general, as you increase in s character, you're going to get shorter bonds because you have smaller hybrid orbitals here. All right, so let's go back up here to this picture of acetylene. Let's see if we can draw it. Now we now know that both of these carbons in acetylene are sp hybridized. So let's go back down here and let me go ahead and redraw the dot structure really fast. All right, so we have acetylene here. So we have carbon triple bonded to another carbon. We know each of those carbons is sp hybridized. Right, so if each of those carbons is sp hybridized, each carbon has 2 sp hybrid orbitals. I'm going to go ahead and draw in 1 sp hybrid orbital. Again, I'm ignoring the smaller back lobe. And here's our other sp hybrid orbital on this carbon. So let me go back and look at our diagram again. Right, so each carbon, let me use red for this. Right, so each sp hybridized carbon has an sp orbital with 1 valence electron in it. I'm going to put that in here. And then there's another one, right? So there's another sp hybrid orbital with 1 valence electron in it. So I'm going to go ahead and put the other electron over here in this hybrid orbital. All right, and also notice, right, if you're dealing with an sp hybridized carbon, you also have 2 p orbitals, 2 unhybridized p orbitals, each p orbital with a valence electron. So let me go back down here, and I'm going to draw in, here's 1 p orbital, right? There's one p orbital with one valence electron, and then here's another p orbital right here with another one of those valence electrons. Right, so now we have our picture of an sp hybridized carbon. So let's say that was this carbon over here on the left, and so now let's go ahead and draw on this carbon on the right. This carbon on the right is also sp hybridized. Therefore, this carbon on the right has an sp hybrid orbital, right, with one valence electron in here, and then another sp hybrid orbital with one valence electron here. This carbon, since it's sp hybridized, right, so once again go back up here to this diagram, this carbon is also going to have a p orbital with a valence electron and another p orbital with another electron in it. So we go back down to here and we draw in those p orbitals. So here's one p orbital, right, here's one p orbital with one valence electron, and then here's another p orbital with an electron in here like that. All right, finally, we have to add in hydrogen, right? So we have a hydrogen on either side here. So we know that hydrogen has one valence electron in an unhybridized s orbital. So over here, we have a hydrogen with one valence electron in an unhybridized s orbital. And now we can finally analyze the bonding that's present. Right, so we know that if we have head-on overlap of orbitals, like right in here, right, that's a sigma bond. So there's one sigma bond. Here's a head-on overlap of orbitals between our two carbons, so that's a sigma bond. And then finally, we have a head-on overlap of orbitals here, so that's another sigma bond. So we have a total of 3 sigma bonds in the acetylene molecule. In the video on sp2 hybridization, we saw how to make a pi bond, right? So we had this side-by-side overlap of orbitals. So here we have one pi bond, right? We have interaction above and below, so that's one pi bond. And then we have another pi bond here. So we have side-by-side overlap of orbitals here as well. And so we have 2 pi bonds present, right? So we have 2 pi bonds present in the acetylene molecule. So let's look at our dot structure again, right? So we saw the bond between this carbon and this hydrogen was a sigma bond, and we saw there was one sigma bond between our two carbons. So I'm just going to pick the one in the middle here, say that's a sigma bond, and then this bond over here we said was a sigma bond. So there's our 3 sigma bonds, and then we had a triple bond present, and so there were 2 pi bonds also present. So 2 of these are pi bonds here. So a total of 2 pi bonds and 3 sigma bonds for the acetylene molecule here. Remember, pi bonds prevent free rotation, right? So we can't rotate about the sigma bond between the 2 carbons because of the pi bond. So there's no free rotation for our triple bond. All right, so we have a linear shape. So let me go ahead and draw that line in here. So you see this linear geometry for this molecule like that. All right, also in terms of bond length, so the distance between these 2 carbons, the distance between this carbon and this carbon, let me go ahead and circle them, the distance between these 2 carbons turns out to be approximately 1.20 angstroms. So an even shorter bond length than in our previous video. So once again, that's due to the increased S character, right? So increased S character gives you these smaller orbitals, and so that's one way to think about the shorter bond distance in a triple bond compared to a double bond or a single bond. All right, so that's a lot that we've covered here. Let's go ahead and draw the dot structure one more time and analyze it using steric number. So we have our triple bonds, and if we're doing steric number to find out the hybridization state, we know to do steric number you take the number of sigma bonds. So let's say our goal was to figure out the steric number for this carbon. The number of sigma bonds, I know this is a sigma bond. I know in a triple bond I have 1 sigma bond and 2 pi bonds. Right, so there are 2 sigma bonds here and 0 lone pairs of electrons. 2 plus 0 gives me 2, so I need 2 hybrid orbitals, right, which you make from 1 s orbital and 1 p orbital. So if you get a steric number of 2, you think sp hybridization. Right, so this carbon is sp hybridized, and so is this carbon as well. And so that's how to think about it using steric numbers. So once again, a linear geometry with a bond angles of 180 degrees. Let's do one more example using steric number to analyze the molecule. Let's do carbon dioxide. So if we wanted to figure out the hybridization of the carbon there, let's go ahead and do that. So using steric number, so the hybridization of this carbon, All right, so the steric number is equal to the number of sigma bonds. So if I focus in on the double bond between one of these oxygens and this carbon, I know that one of these bonds is a sigma bond, right, from our previous video. So I have one sigma bond here, and then for this other double bond on the right, I know that one of them is a sigma bond. Right, so I have two sigma bonds here and 0 lone pairs of electrons around the carbon. So 2 plus 0 gives me a steric number of 2. So I need 2 hybrid orbitals for that carbon. And of course that must mean this carbon is sp hybridized. So this carbon here is sp hybridized as well. And therefore we know that this is a linear molecule with a bond angle of 180 degrees. And so once again, steric number is just a nice way of analyzing the hybridization and also the geometry of the molecules. And so in the next video, we'll look at a couple of examples of organic molecules in different hybridization states.